Let's talk about the Poisson's ratio. So in this video, we will answer what is the Poisson's ratio, what is the equation for the Poisson's ratio, and we will do a practice question, an FE type question covering the Poisson's ratio. So number one, what is the Poisson's ratio? So the best way I can explain this is by actually looking at a physical example. So let's say I have this rubber material here, and what I'm going to do is give it a length. So I'm going to denote a certain length that we're focused on, and the length in this case will be between my fingers. So just you can think of it as just the initial length or the gauge length, the initial length. So this is the gauge length, and then what I'm going to do is give it a load, a uniaxial load, a tensile load or a tensile force in both directions. And that's basically the force that my muscles are going to supply, the load my hands or my muscles give to this rubber material. So now if you look closely, watch it with me. So I'm going to apply a load, and I want you to look at what's happening. So we have two things going on. What are those? We have an increase in length. In other words, we have a change in length in the longitudinal direction, the axial direction. And now, if you look very closely as well, we have a reduction in width in the lateral direction, up and down. Once again, you have an increase in length or change in length in the longitudinal direction. And at the same time, let's do this again. We have a change in width in the lateral direction. And that tells me, since we have a change in length, we can get the strain in the longitudinal direction. And since we have a change in width in the lateral direction, we can get the strain in the lateral direction. From there, we know that the Poisson's ratio is simply the ratio of the strain in the lateral direction divided by the strain in the longitudinal direction. Now with that, let's look at this fill in the blank FE type question and solve for the Poisson's ratio using the equation. So let's read this slowly. We're told a steel rod has a gauge length and diameter of 4 inches and 0.475 inches respectively. So now I want you to look at the first sentence and start denoting variables. So I'm gonna denote that as the given. So we know it's a steel rod, and we know that it has a gauge length and diameter. This is common, the way they denote it in their problem statements on the FE. Gauge length comes first, it's 4 inches, diameter is second. So what I'm gonna do for gauge length, let me just call it L. You can denote it as L naught, L initial, Li. Let me just call it L for the gauge length. Gauge length, just think of it as the starting length, the initial length. So that's going to be 4 inches. Let me write that here. Then we are told that the diameter, let me call that D for the initial diameter, is 0.475 inches. So that is done. Then we're told the modulus of elasticity is 29,000 KSI. So in this case, we have a modulus of elasticity, which is always our E value, is 29,000 KSI, kip per square inches. At the proportional limit, the rod is subjected to a tensile load of 6.85 kips. So we know the load in this case, let's call the load P, sticking with the FE handbook, that would be our P value is going to be 6.85 kips, K for kips, resulting in the rod being elongated by this amount and the diameter is reduced by this amount. So we have, just like what we showed it with that rubber, you have an elongation. And note, when they say being elongated, that's not the final length. That is a change in length. Elongation is along the longitudinal direction. So the change in length in this case is that, so that would be delta L. Delta means change in length. Change in length is L final minus L initial. So we know that is going to be what that means. It's a change in length, 0.084 inches. And then lastly, we are told we also have a diameter is reduced by this amount. So it's a very, very tiny amount. It's small. So it cannot be the final diameter. It doesn't make sense, right? Because the initial diameter was this amount. The starting diameter was this. So the final diameter will probably be 0.42 or something close to that. So this would have to be what? A change in diameter. It's a change in diameter, not the final diameter. So that would be the change in diameter, which is this value of 0.00630 inches. So now we have everything denoted as we're given, and the Poisson's ratio is what? We know, fill in your response in the blank. To fill in the blank question, common nowadays on the FE. So whatever we get, make the best educated answer and put that in there and move on. Don't overthink it. Put an answer. They're likely to have multiple answers, and for the most part, it's usually whole numbers for these fill in the blank. So let's just do that and go into that solution. So let's denote what we want to find. We want to find the Poisson's ratio. Find. Let me actually write it in this case for us. So Poisson's ratio. And we know we can give this a certain letter. Per FE handbook, I want you to pause the video and find the equation for Poisson's ratio. It's in the FE handbook. So pause the video and let me show you the equation. And we know it's going to be on pages 130 and 131 if you're using the PDF for the latest FE handbook. So we know we're going to refer to this definition. That's why I brought it here. But the Poisson's ratio will be this equation. We have a negative here. We'll discuss that as we continue. It's the lateral strain over the longitudinal strain. For the most part, ignore this negative. Just use the lateral strain over the longitudinal strain. Almost all materials have a positive Poisson's ratio. Unless you have a different kind of material, which is usually not the case, almost all materials will have a positive Poisson's ratio. So lateral strain over longitudinal strain. And notice it's this italics B. So let's denote that up there. So what we know is it's going to be, this is what we want to find, the italics B. Now for the solution, what I'm going to do first is actually draw a picture for us just to help us visualize what's going on, just like what I did with that rubber initially. So we know we have what is the object in this case. We know it's going to be a steel rod. So it's going to be this, a steel rod. And the rod has a diameter. So we know it has a diameter and it has a length. So let's try our best to actually draw something like that, just to help us visualize what we have. So we have a rod, and this rod, I'm making it thick just to make sure we see everything here. And we know it has a diameter, and the way I denoted the diameter is like this. And let me call that the diameter, capital D. Note this is the starting diameter of that amount, and that's denoted the second number, right? 0.475. 475, and I'll denote this for inches. That means inches. So then we know that's the diameter, and it also has a length, right? It has a starting length, and this is going to be the length, and let's call it L, just like what we did. You can call it L naught. The FE handbook uses L naught, but let me keep it simple. Let's keep it L, and that's going to be 4 inches. And let me denote inches like this. So then we know this thing, the rod, is going to get subjected to a load here, right? That's going to be the load P, and it occurs at the proportional limit. All that means is we're loading this thing in the elastic region, which is usually the case, and this is the case that we want. When we calculate the Poisson's ratio, when we find the modulus of elasticity, when we find the stress, we want to always, all those equations under that mechanics and materials section are for that elastic region. We're focused within that elastic region. So we know the proportional limit is in the elastic region. In fact, what I can do for us is draw something real quick. And let's assume we have a tensile ductile material. So let's say we have a ductile material. Steel is a ductile material. And we know we have the y-axis will be the stress, x-axis would be the strain. So stress-strain diagram, we gotta know this stuff. Stress means sigma, strain means epsilon. And we know for a typical ductile material, it looks something like that. The linear region is the elastic region. Then we know we hit the proportional limit. So let's call this the proportional limit. And let me call that sigma PL. Sigma means the stress which is the proportional at that proportional limit point. Then we know after the proportional limit, we will hit the yield point, and let's call that sigma y. Then after that yield point, we stay flat, flat, flat. Then we hit the ultimate, so let's call this sigma ultimate. That's the ultimate stress. Then we know we rupture at the end. Let's call it sigma r for rupture or failure at the very end. So notice the proportional limit is within that elastic region. The elastic region would be essentially the linear region. The proportional limit is in there. That's all that's saying. We're loading this thing in the elastic region. And I just want to note one thing, just to actually note that you have the proportional limit, you have the yield point after that. The yield point doesn't come before the proportional limit. In fact, there's also something called the elastic limit. For ductile materials, steel, we usually say the elastic limit, let me denote it here, sigma elastic for EL. Actually, let me just write it, elastic will equal to sigma yield. Because differentiating both of them is so hard, we just say they're both the same. But the order of these usually, well, always, it's going to be the proportional limit that comes first. Then what comes after that is going to be the elastic limit. Then after that, we know what comes is going to be the yield, sigma y for yield. So just note that, and that is more on the concept side. But in this case, we're in the elastic region. Then we know, what else do we have? We have the load. Let me actually denote the load on the diagram. I'm going slow here for a reason. So the load is going to be how much? 6.85. And that would be kips, and it's loaded uniaxially. 8 kips, tension load. Then what else? We can now denote that very important part in terms of how this thing is going to change along the lateral direction and how much it's gonna elongate, the elongation along the longitudinal direction. And the way we can denote this is the following. We know when we load this, it's gonna look something like this, where the final location, the final part is the red dashed line that I'm denoting. And we know this is the final diameter. So what we know in this case, we have a change in length, and that change in length that elongated this part. So that change in length is this. So we will denote that here. This is going to be delta L. And let me denote delta L here is that value of 0.0084. That's going to be our delta L in inches. Delta L is that. Then we know our delta D has to be the change in the lateral direction. The diameter, the cross section gets smaller in the lateral direction. In the longitudinal direction is delta L. So we know that delta D, we can actually denote it simply, so we can keep it simple and just denote it like this, just to save time and not overthink stuff. But this is delta D, and we will say that's 0.0006 inches. So now I want to say something here, that this reduces in diameter or in cross section, and I just denoted it at the top. That is fine when we're doing the calculation. It'll get us the answer. But we know this delta D is actually split in half. When you want to look at it in actuality, it would be like this part would be delta D divided by 2, and this part at both sides would be delta D divided by 2. So that would be the case. So based on that, it would be 0.003 on the top, a reduction, and 0.003 at the bottom. The same is actually true for the length. I just denoted the change in length on one side to keep it simple, to actually just do the calculation and move on. But we know the change in length would actually occur on both sides. So this side would have a change in length divided by 2, and this side would have a change in length divided by 2. Now with that, let's use the Poisson's ratio equation. So let me get that, and just to know, it's in the FE handbook, and it's defined this way, exactly like this. So let me go above and denote that as italics V, and we know italics V, the Poisson's ratio, is going to be the negative lateral strain and we divide by the longitudinal strain. Longitudinal strain. And we know what is another letter for strain, or what variable do we give that? What letter? We know that is epsilon, right? Stress strain diagram. So we will say negative epsilon lateral, LAT for lateral, divided by epsilon, LONG for longitudinal. So now we just need those two and we're done. So let's actually find the easier one first, the longitudinal strain, the bottom one. And the way you would do that is apply this equation. We know the fundamental definition of strain, assuming we're stretching something, or we apply a force in the longitudinal direction along its length, that is strain, right? Strain is the change in length divided by the initial length. And just note that initial length, or the original length, is our L value. We denoted that. And the change in length, that is given. That's the elongation after we subjected this rod to a certain load in kips. So that's what we do. We just apply that equation for the longitudinal strain. So the strain in the longitudinal direction is going to be the change in length over the initial length, L naught. In our case, L naught is L, so let me just denote that for us, divided by L. So we know the change in length is what? That is given. It's the elongation. It's the elongation elongated by that amount. So we just put that on top, and that would be 0.0084 inches divided by the initial length, which is that. It's the gauge length of 4 inches. Then we can do the math for this, and we get that. So let me do this with you in the calculator. So what we would do is do the fraction symbol there, and I like to put stuff how I see it and how I write it. So we do that and divided by 4, and that equals to 21 over 10,000. So let's break this down into decimal form. You click that. I have scientific notation. Usually I don't like seeing that. Let me actually write that for us. So it's 2.1 times 10 to the negative 3. And the inches cancel. It's unitless. It's inch per inch for the strain. But we know 2.1 times 10 to the negative 3. All it says is you move 3 to the left. So 0, 0. So how that would look is going to be equal to 0.00210. And that would be the strain in the longitudinal. So now we're almost done. We need just the lateral. But that one is a little bit more tricky. But the same fundamental idea behind strain, the basic definition of strain, would still apply. And simply, in the lateral direction, we know what happens is it's a change in diameter. So it's no longer a change in length, it's a change in diameter. So how would you get the strain in the lateral direction? We take the change in diameter divided by the initial diameter, the original or starting diameter. So let's write that equation. So epsilon lateral equals the change in diameter divided by the original diameter. We know the change in diameter in this case is given in the problem statement to be 0.0006 inches, and the starting diameter we know is 0.475 inches. Let's use the calculator to solve this. So with the Casio. So now before I solve this one for the lateral strain, I want to quickly store what I got for the longitudinal strain. Remember, it was this divided by that, that divided by that. We got that as the answer, because I know I'm going to use it in my final calculation. And you'll see what I mean as we continue. So let me store this answer. And what I'm going to do is store it in A here, box A. We have the option store in A, B, C, D, or F through F. So I'm going to focus on storing that in A. So the way you do that is STO function. So you have to click Shift, STO. Now it's asking where do you want to store it. Be careful, don't click alpha A, B in the pink. All you have to do is click one of these. So I'm just going to store it here, and you just click that in A. Yes, answer, store it in A. That's what we want, and it did it. You don't have to do nothing else. Then you can press all clear or just continue with your calculation. So now let's actually do this calculation for the lateral strain. So we take 0.0006 divided by the 0.475, And for that one, you should get a value of that. We reduce it to a decimal. So it's about 0.00126. So that's that. Let me store it. Let's store that in B. So the way you would do that is we do the same idea, shift STO. Where do we want to store it? Even though it doesn't ask, this is the question that we should be asking in B. And then it stores it in B. So then what we can do finally is, let me actually write this down so we can see the value. It's approximately 0.26. So that's the lateral one. And we know this lateral one, just note, is a negative. This is where the negatives comes into play. But if you're confused about this, just always get a positive answer for the Poisson's ratio. Usually it's positive, but it's negative in this case for the lateral because it's a reduction in diameter. The diameter gets smaller, so it's a negative strain. Here in this case, this was a positive length, change in length. Increase in length is positive based on our positive sign convention. So that we have to put a negative, then we put a negative times a negative gives us a positive. I know that's a little confusing, but that's why at the end we should get a positive. If you're confused about that, just most of the time it's positive for the Poisson's ratio, unless you have a certain other type of material with negative Poisson's ratio, which is not often the case. So it's going to be negative for that one. So then what I'm going to do is solve for the Poisson's ratio. We take E lateral, the negative. I can keep that negative, and we should. Negative times a negative, 0.00126. Negative times a negative is a positive, right? And E longitudinal would be that value, 0.00210. So now we can do the math, or what I'm going to do is do it just in the calculator based on what I stored. Here we're practicing how to use the calculator. So what I'm going to do is remember that E lateral was going to be what we found for the second part. So that was B. So we stored it in B. So all we do to get B, it's in pink. You have to do alpha B. That's going to be the lateral one, the strain lateral. And now for the strain longitudinal, it was A, the first calculation. It was this one. So we do alpha A and then equal. We get the answer. Reduce that. We get approximately 0.60. 0.60 should be the answer. So that would be the Poisson's ratio. Now if we go above, all we do is fill in the blank 0.60, and on the actual exam you will type 0.60. So you can't put 0.601. I bet they have that as a correct answer as well, and multiple correct answers in a range. So they have it in the back end in the program that they use or to create these questions. I bet that's the case. And usually you want to use your best engineering judgment for these final answers and make a good judgment. Usually you want to go for a whole number. In this case, my judgment and my final answer would be 0.60 for the Poisson's ratio. And that's all for this one. I'll see you in the next video, and thank you for your practice.